Okay, we are on to 5.6, part 2, okay, basically just the last half of our notes here. We have to go back to this idea on what a function is. If you remember a function, the definition of a function is a relation, a way of relating x to y, a relation where every input has only one output. Okay, so every input can get you out only one output. And if you remember, one way of determining that is we did that vertical line test. If you remember our vertical line test on the graph to determine if every input has only one output. Okay, so what I've done here is here I have the graph of y equals x squared. That's this blue graph right here, a nice quadratic. And I've also graphed its inverse, meaning I flip-flop the x's and y's, so it's an x equals y squared. Okay, we flip-flop the x's and y's. So these two are in fact inverses of each other. If this is f of x, then this here would be f inverse of x. Okay, they're inverses of each other. But what I want you to know is if I look at the blue passes the vertical line test. Okay, it only ever hits the 1 point. Okay, but what about this red? Okay, if we look right here on this red, let's just draw one vertical line in. On its inverse, it has two outputs for one input. When I put in a 3, it has two different outputs. Okay, so this, in fact, this guy right here is not actually a function. It's not actually a function because every input, I have an input with two different outputs. Okay, so yes, here's my blue function, f of x, but its inverse is not actually a function. Okay, unlike over here, if you look at this blue, again, these two are inverses of each other. This is the x cubed function. You can see right there a little, this is x to the third. This one here's the cube root. So these are in fact inverses of each other. This is f of x. This is f inverse of x. And if we look at the blue only ever touches one line, 1 point the whole entire way through. And the red only touches one line, 1 point the whole entire vertical line test through. So both of these are functions. Okay, so sometimes a function's inverse is not a function, like a parabola. All parabolas, whether it opens up or opens down, its inverse is not a function. So to be able to find that inverse and write it in function notation, what we have to do is then restrict the domain. Meaning, just look at one part of it. Because if I was to cut this in half, sure, that would have the inverse. I can flip it. If I was only to cut this one in half and this one in half, we can see there, if I was only dealing in quadrant 1, sure, that function has an inverse. Both of them are going to pass that vertical line test. Okay, so that's why we restrict the domain on these. So here when it says to find the inverse of f of x equals x squared, where this little bit of information here, x has to be greater than or equal to 0. Meaning I'm only putting in positive values of x. So when I graph this function, this means I'm only graphing positive values of x. So this is a quadratic. We know it's a quadratic opening up with the vertex at 0, 0. So if I graph the actual function, if I graph this, it's going to be the point 0, 0, 1, 1, 2, 1, 2, 3, 4. It's only going to give me this 1/2 of the parabola because we're only dealing with x is greater than 0. Okay, so then when I find the inverse, okay, so I'm going to find the inverse using flipping my x's and y's. So here's my function, y equals x squared. So when I flip it, we'd have x equals y squared. Flip the x's and y's. And I solve this now. I'm going to need to square root both sides. So I'd have y equals, normally here we'd go plus or minus square root of x, right? When you square root both sides, we get that plus or minus. But we're only dealing with positive x, which means that we're not going to be dealing with that negative part, and it's just going to be the square root of x. Oops, sorry. So the graph of this, again, we're going to have that reflection. So instead of the point 2, 4, it's going to be the point 1, 2, 3, 4, 2. We're going to have it look like that instead. So we still get that line of reflection, but we're only talking about that 1/2. Basically, we're cutting this and only dealing, excuse me, with those pieces. Okay, so we restrict that domain a bit. Okay, so one way of telling if whether a function and its inverse are both functions is instead of just doing the vertical line test, we do the horizontal line test as well. So this function here is a function because it passes the vertical line test. But now we flip it and do the horizontal. So this tells me that its inverse is also a function. Okay. It tells me its inverse is also a function. Whereas this one over here, it passes the vertical line test, so the function, this actual graph is a function. But if you notice this horizontal line test, here it has 2 right there, so this tells me its inverse is not a function. So when we actually find its inverse, it's not going to be a function itself. Okay? When we flip-flop those x's and y's, we're going to have this plus or minus issue. Okay? Right, so now let's go ahead and let's consider this function. Consider the function f of x equals 2x to the third plus 1. Determine whether the inverse of f is a function, then find the inverse. So let's determine, is that inverse a function? So let's go ahead and I'm going to do that by graphing it. So I'm going to look at 2x to the third plus 1, and we're going to look to see if it passes that horizontal line test. Okay, so it's this quadratic that's going up forever, so horizontal line test, yep, it's only ever going to touch 1 point. Even through here, it's always going down a little. So is the inverse of this a function? Yes, it is. So now to find that inverse, I'm going to rewrite this as a y equals. Okay, so there's my original function. Now its inverse would be replace my x's with y's and my y's with x's. X equals 2y to the third plus 1. So there's the inverse. So this is the inverse. But now I need to solve it for y. So subtract the 1 from both sides. X minus 1 equals 2y to the third. Divide both sides by 2. So we would have y to the third equals x minus 1 over 2. And then now we need to cube root both sides. So my f inverse of x would be the cube root of x minus 1 divided by 2. And so I'm going to double check this in my graph. I'm going to graph this. It's to the 1/3 to make sure we have that symmetry. Okay, so now to graph this, I need to put this numerator in parentheses as well. Parentheses x minus 1 divided by 2, close that parenthesis, to the 1/3. And zoom, I'm going to square up my screen 5, so that way my intervals are the same. So there's my function. Here comes its inverse. Yep, and we have that nice line of symmetry coming through at a diagonal there. Okay, so there is my inverse. Okay, next consider the function f of x equals 2, the square root of x minus 3. Determine whether the inverse of f is a function. Again, I'm going to look at the graph here. So my 1, 2, the square root of x minus 3. Okay, so let's see, it's going to give me this opening up like that for forever. Yep, it's going to pass the horizontal line test, so yes, it is a function. So now we need to find its inverse, so write this as y equals 2, the square root of x minus 3. Okay, and now flip-flop your x's and y's. X equals 2, the square root of y minus 3. Okay, so this is 2 times that, so I'm going to divide both sides by the 2. X divided by 2 equals the square root of y minus 3. To undo a square root, I would need to square both sides. X squared is x squared. 2 squared is 4 equals y minus 3. And then we'll need to add the 3 to both sides. So my inverse function, f inverse x, is going to equal x squared over 4 plus 3. One thing to notice now, if I'm going to graph these two, let's graph this other one. So we have x squared divided by 4 plus 3. Okay, I get this. Let's just do a straight old zoom out from the center. Oh, I don't know what happened there. Okay, if you notice, this one has the 1/2. This one has the whole thing. This has a piece that's extra. Where did that come from? Okay, if you notice this original function here, the domain of this original function is only numbers greater than 3. This original function's domain is x has to be greater than or equal to 3 because we have an even index here on the square root. So x has to be greater than or equal to 3. And if I try tracing on that original function, I can't put anything less than -3. I put in a 0, nothing works. Put in a -1, it doesn't work. So I can only put in numbers greater than or equal to 3. Okay? And I'm only going to get numbers out. My range is numbers greater than or equal to 0. My range for this function here is y then is going to be greater than or equal to 0. So that means that on its inverse, my domain is now the range from here. X's can only be greater than or equal to 0, and my range is y's greater than or equal to 3. Oh, not 0, 3. Because my domain becomes my range becomes my domain. Again, range is always y, domain is always x. Okay, so that means that actually on this, I can't put these zeros, these negatives in. So it's only this half of the graph. Okay, because my domain is x has to be greater than or equal to 0 because that was the range of the function that now becomes the domain of the inverse. Okay, so that's something important to note there. We need to know that domain if there's that domain restriction. So I highly encourage you always to graph these, to check them, to make sure you don't have any domain and range issues. Okay, all right. Okay, example 6. Here we want to verify that f of x equals 3x minus 1 and g of x equals x plus 1 divided by 3 are inverse functions. Okay. One way of doing that is to put one function inside the other. I'm going to put g of x inside here for x and see what happens. So basically I'm doing f of g of x. So instead of taking 3 times x, I'm going to take 3 times x plus 1 divided by 3 and subtract 1 on the end. Okay. So then here these 3's divide out. I'm left with x plus 1 minus 1. I'm left with just plain x, which tells me that whatever I put into this, if I then put it again into that, it's going to undo it. Okay, I get back to where I started. I put in an x, I get out an x. Okay, but then I also need to do it the other way around. I need to put this, let's switch colors, this in here for x. So instead of x plus 1, I'd have 3x minus 1. Plus 1 all divided by 3. So this is me doing g of f of x. Okay. So that minus 1 plus 1, so I end up with 3x divided by 3. The 3's divide out, I'm left with just an x. So here again, input of x, output of x, it's not going to change what I do. So there I verified it. So yes, f of x, I would say f of x and g of x are inverses. Okay, our very last example. Okay, find the inverse of the function that represents the surface area of the sphere. Okay, so one thing, word of caution here, big word of caution. When the variables have a context, what I mean by context, they represent something. You cannot switch them. When the variables have a context, you cannot switch them. So this example 7, I guarantee people are going to be getting practice and skill checks wrong on this, is they're going to try to flip-flop the variables when they have a context. Like here, S represents surface area. R represents the radius. I cannot just flip-flop the radius and the surface area. Okay? Because then the equation will not make sense at all. Mainly to find the radius, I take 4 pi times the surface area squared. That makes no sense. So when it has a context and you need to find the inverse, okay, what you do on this is you do basically what we did in this process here. You just don't flip-flop the variables. You solve for the other variable. Solve for the other variable. What we mean by this is this variable is solved for s because it's s equals 4 pi r squared. This is 4 pi times r squared. For me to get the inverse, my final answer down here is going to be an r equals something because r is the other variable in there. I want to solve for that, so I want to get that r by itself. Right now this is 4 pi times r to the second. So to get rid of a multiplied, I'm going to have to divide. I'm going to have to divide both sides by 4 pi. So these divide out. So I'm left with r to the second equals s divided by 4 pi. So now I'm going to need to square root both sides. So normally when we square root, we have plus or minus. But think about the context of the problem. Does a negative radius or negative surface area make sense? The negative does not make sense in this context. Okay, now if we were talking about maybe distance or something, we could go negative, but in, not distance, like velocity. Sorry, velocity, we could go negative. But we cannot go negative on a radius. Okay, so the negative doesn't make sense. So my r then would equal positive the square root of s divided by 4 pi. Okay. So there is my inverse function, because my original function was s equals something in terms of r. My new function is r equals something in terms of s. So now how this can be used is for this last bit, then find the radius of a sphere that has a surface area of 100 pi square feet. This information they give me here, this guy, is my s. So now all I need to do is plug it into here for s. R equals the square root of 100 pi divided by 4 pi. Well, pi's divide out to 1. 100 divided by 4 is 25. The square root of 25, r then would equal 5. So the radius is 5 if the surface area is 100 pi square feet. Okay, be very careful on the context problems. When the variables have a context, meaning they're representing something, you cannot just switch them. Okay, it doesn't work that way. Okay, good luck.